I was muted,
Our,
not anymore. Good.
well, our next speaker is David Bernal from Carnegie Mellon University. He is a PhD student in the chemical engineering department and in the quantum computing group. He's collaborated with the Tepper School of Business and works in discrete optimization and in many, many other topics. And he's got a very wide portfolio that he can talk about himself better. But one of his most recent things is he's been working a little bit in quantum computing and taught a quantum integer programming class recently, which I thought was very interesting. With that, I'd like to let David take it away. You have 20 to 25 minutes and there'll be questions afterwards. Thank you very much.
Thank you, Alex, and thank you, Elias, for the invitation. Thank you, all of you, for sticking around on a Friday afternoon for this seminar. I hope to entertain you with this talk on modern computational approaches to nonlinear discrete optimization. So I'll cover several fields, and you will feel at least in some of them that you know everything. In some others, you will feel that you know nothing. It's going to be super exciting. So let's start. If this thing moved, there you go. So we all know that looking for optimal solutions in the real world is time consuming, expensive, and prone to errors. Therefore, that's why we like having these mathematical models that reflect our knowledge on the system, on the world, right? And that incorporates assumptions, simplifications, and hopefully balances tractability and validity, right? And obviously, we are all familiar with mathematical programming and we love writing objectives and constraints in terms of mathematical equations with respect to certain variables, right? But the word itself is abrupt, unexpected, discontinuous, non-smooth. So how do we deal with this? And the tool, the answer, as most of us might know, is it can be integer programming or mixed integer programming. And this can be seen as this universal tool for modeling non-convexities and discontinuities because we allow certain variables to only take discrete values. And obviously this appears in practice, right? I mean, there are certain objects that are indivisible, therefore you cannot talk about 2.3 people, but they are mainly useful for as triggers or switches to encode logical conditions, disjunctions, implications, precedents, and that's where many people use it. Like they appear all over decision making, and they can be even called, according to late Professor Balazs's word, ubiquitous or omnipresent, right? So, but let's go a little bit further and say, what about the actual real world? So the real world, a part of being abrupt, is nonlinear, right? So we can, although it would be enough only to have the nonlinearities, we can summarize more of that information with all of that with discontinuities. We can summarize better our models with nonlinearity. And that's that assumption that the objective and the constraints can be written as a linear combination of the variables doesn't hold in general, but this only makes our lives harder, right? So now that I've talked about this, let's define formally what I will like to talk about, which is discrete nonlinear optimization, or for those of you that are familiar, mixed integer nonlinear programming, right? And it has an objective function constraints, and some of the variables of any of those can be nonlinear, and some of the variables are constrained to be discrete. So I come from a chemical engineering department. So in process systems engineering, we have several applications for this kind of optimization problems. So process synthesis, process operations, process control, molecular design, but these are not exclusive from process systems engineering, right? There are applications in medicine, in other branches of engineering, such as civil engineering, operations research in general, network design. So, and to the question, like, what can I model using MINLP or discrete nonlinear optimization? Short answer is everything. And how is that? Well, you can encode any Turing machine, including universal ones, using MINLP. Cool, right? So then you start wondering, why don't people use this more widely, right? I mean, it can basically every problem is an MINLP. And the short answer is, well, I mean, computational complexity wise, it might not be the most appealing case, right? It's NP hard, and in some cases, it can even be proved to be undecidable. But we still need to solve these problems in practice. And this part, I won't spend much, but we all know that enumerating is not practical, right? I mean, it's out of the question. You can spend the age of the universe trying to enumerate tiny problems. So how are these problems usually solved, right? And we all know branch and bound. You solve the continuous relaxation of your problem, then you start as computer scientists. We love looking at trees that grow downwards, and in each one of these roots, you start enforcing discrete values to the variables that are supposed to be discrete. And this whole idea is divide and conquer, right? And these are enhanced with cuts or extra inequalities that give you extra information to avoid enumerating the whole tree, which would again yield this total enumeration that we want to avoid. And we all know that this has been super successful for mixed integer linear programming, right? In the course of my lifetime, there has been a 2 million X algorithmic speedup with these kind of problems. So we might be familiar with this kind of plot from, I don't know, from the big names in our field. How about mixed integer nonlinear programming? So you can still design a branch and bound algorithm for nonlinear problems, but another way to approach this is through decomposition methods, where you basically piggyback on the success of MILP and cleverly break down your problem into sub pieces that you can address more efficiently. And then by gathering the information and having these games between the sub problems, you can solve these problems more efficiently, right? And that's where at least my research group has been working a lot. So let's talk a little bit more about that. We're an MINLP, right? And then first we just saw MILPs, you can solve them efficiently. On the other hand, there is this subset of the variables that if you fix them, the remaining problem becomes way easier. In this case, the discrete variables. Now you would end up with a continuous nonlinear optimization problem. So obviously, I don't know, it sort of makes sense to break the problem in this way. And from the complexity, you can also make like a hand wavy argument saying like, okay, well, if these problems are NP hard, you rather solve several times problems of a fraction of a size that a single time the big problem, right? So, okay, taking this into account, my PhD advisor, Professor Ignacio Grossman, back in the 80s proposed this method, the first method back then for MINLP, which is the outer approximation method, which basically approximates nonlinearity with a first order Taylor approximation. And then you separate everything into a continuous nonlinear problem and a discrete linear problem. And iterating between the two of them, you can find the optimal solution of these problems. So this is not like a normal talk. So I'll introduce myself now. Yeah, who am I, right? And why am I talking right now? So I'm doing my PhD at CMU, as Alex said, with Professor Ignacio Grossman. I have an undergrad degree in chemistry and physics and a master's degree in chemical engineering. And I have been lucky enough to have some experience during my PhD working at ExxonMobil Research and Engineering. And I was part of the Feynman Quantum Academy Fellowship at the NASA Quantum and Artificial Intelligence Lab. And that's how I got into this whole business of quantum computing, right? So what have I been working on? I have been lucky enough to be in a department that talks a lot to people in industry. So I have been exposed to many super cool problems like refinery optimization, maintenance, scheduling, catalytic distillation, right? And even applications outside of chemical engineering, which is, for example, compiling for quantum annealers, which is what I was doing at NASA, right? I have worked on the MINLP theory and algorithms, which is what I will discuss later. I basically like to use cool math to try to address these problems. So conic programming and algebraic geometry are two of the things that I have been looking at, hoping to share this in open source software as much as I can. So I guess I have been fortunate enough to be able to do this. A little bit on process intensification. And the last chunk of it is quantum optimization models and algorithms. We're already at a stage where quantum computers are there for us to start playing with it. And if you are familiar, a single problem can be written in several ways, right? So just trying to figure out which of the formulations works better on a quantum computer, given the algorithms that are available for this kind of machines, is a completely new and super exciting research field. So, I mean, this is an open invitation too. Anyways, back to MINLP. So what have I done so far? I did a solver benchmark just to realize which techniques work. The main outcome is that not a single technique works for every single problem, which is good because this means that there is still work to be done on mixed integer nonlinear programming. Some algorithmic improvements from that algorithm from the 80s from an outer approximation, and commercial and open source software implementation of MINOPs. And I would definitely love to have a talk on these topics, but that's not what you came for, right? So let me switch gears and start talking about another thing that also fascinates me, which is physics. So here comes the fun part. I don't know if you knew, but if you have a magnet and you heat it up, it stops being a magnet past a certain temperature. That thing is called a phase transition. And this was observed by Pierre Curie. Now the temperature is called the Curie, is known as the Curie temperature. And this is completely nuts, right? If you think like just at a very precise point, there is this sudden change in the way that nature behaves that will obviously blow everyone's minds. And maybe a way of understanding a magnet is this picture that I have here. Let's assume that there are teeny tiny magnets there that they can point north or south. So north is green, south is red. And you would agree with me that since this picture is mostly green, this magnet, it's actually a magnet, right? It's magnetized towards north. Past that temperature, things start to shuffle, and suddenly you end up with like as much red as green. So in average, this thing is no longer magnetic. Well, this exact same model is what Lenz came up with in the 1920s, and he gave it to his PhD student Ising, who not only solved the 1D case analytically for this kind of model, but also gave the name to the theoretical model. Now we know it as the Ising or Ising model. 20 years later, Onsager, who later won the Nobel Prize, solved analytically the 2D case. And much later in the 2000s, it was proved that in 3 dimensions, this problem cannot be solved analytically. Basically, the way that it was proved, it's that it was equivalent to a max cut problem. If you're familiar, that's an NP-complete problem from graph theory. So from the physics point of view, this was cool because Wilson in 71, later he got a Nobel Prize for that, came up with this notion of universality, where systems that have the same number of dimensions and symmetries go through identical phase transitions. And this model is the simplest one on the theory space that is able to explain this kind of phase transitions. Why do we care? Well, going back to MINOP, if, now hear me out, this mathematical model that we have over here has only binary variables. So let's assume that it's no longer mixed integer, but it's still integer. All the nonlinearity is quadratic, and it doesn't have any constraints. We know this as a quadratic unconstrained binary optimization. This is a subcase of MINOP, which still retains the combinatorial part of it. So this is interesting, right? I mean, I wish we could solve this because at least we could solve a subcase of MINOP. How do you actually solve this? So I thought I was gonna be the only one speaking about famous physicists, but then Alfredo came up with Heisenberg, so he took that from me. But let me start with the adiabatic hypothesis by Einstein, which basically says that if you have a system and if you allow it to evolve adiabatically, you can go from any state to other state. And more practically speaking, assume that you have a system. You allow quantum interactions, and then that system is sitting in an energy state. And that energy state has a ranking, let's say the lowest one, because we're interested in the lowest energy states. Then you allow that thing to evolve, to go through a Schrodinger evolution, no measurement, no noise, 0 Kelvin, sufficiently slow. And after the evolution, you go open the box, and this new system is going to be at a state that has an energy at the same ranking. In this case, the lowest energy state. How is this useful? Well, you can come up with an algorithm to optimize. How? The final state, what you're going to do is that you're going to encode your optimization problem. So you know the optimization problem that you want to solve. You just don't know how to solve it, right? So that's going to be your final state. On the other hand, you're going to have a state that you know its lowest energy, a system that you know its lowest energy state. So you set that up, and then you let that thing slowly evolve up until it gets to the system that you're actually interested at. You open the box and check inside. And there you have the solution to your optimization problem. So that's the adiabatic quantum computing part of things, right? And this is, again, this is a property of the Schrodinger equation. So this is literally a property of how we understand the system, the behavior of these systems. How do you do this in practice, right? Well, we use quantum computers, easy, right? There is one model, which is quantum annealers. Maybe if you haven't heard of this, these are machines that implement a single kind of quantum algorithm, which is called quantum annealing, similar to simulated annealing, if you're familiar with that. And you can understand this as a finite temperature implementation of that adiabatic quantum computation algorithm that I just told you about. So we cannot go to 0 Kelvin, but these guys try really hard and they go to 15 millikelvin, which is quite cold, and they just go through this evolution. And at the end of the day, you open up the box and you measure. That's a way of doing that. Maybe you have heard of D-wave quantum annealer. Another way of solving QUBOs, right? Because we're still thinking in QUBOs right now. The way that you interact with these quantum computers is through QUBOs. So another way of solving QUBOs with quantum computing is using the so-called gate-based computers. So these, what are gates? Gates are quantum operators. They are just the way that algorithms are implemented into these machines. There are the two best known algorithms for solving QUBO are the quantum approximate optimization ansatz or algorithm, QAOA, or the variational quantum eigensolver. And a way of understanding them, right, because of time issues, I cannot go completely in depth in here, is that you're assume that this is the adiabatic pathway. This is the way that you go from this initial deorganized state that you know the lowest energy to what your actually objective function means. This is the adiabatic pathway. And these algorithms, they try to implement a discretized version of this. So that's more or less how it works, right? So maybe you have heard of Google and IBM coming up with this kind of computers. They implement gate-based computers, and you're able to implement those algorithms in them. So do they work? That's a great question. So on the quantum annealing side, these are results that recently published from people at Los Alamos. On the y-axis, you have the optimality gap. On the x-axis, you have the runtime in seconds. You're interested in the green line over here, which is the quantum annealer. All the other lines are classical alternatives. And if I zoom in, you can see that the quantum annealer is able to achieve a solution better in terms of optimality gap in orders of magnitude less time, right? Now, we're optimizers, and obviously anyone can come up and say, oh no, this is a heuristic, there are no guarantees, these are limited by size, by connectivity. It has its issues, but you cannot say that this doesn't have potential, right? On the other hand, on the gate-based computers, those are also cool, especially QAOA. It's an approximation algorithm, and I'm glad that Alfredo went before me, so he defined all these approximation ratios and all that stuff. When these algorithms were proposed, they had the best approximation ratios, even better than any classical counterpart. So very interesting from the theoretical guarantees. These are even more limited from size and noise compared to the quantum annealer. So we have tinier chips, but they are obviously interesting, right? So we better look at them. So the state of the affairs as of December 1st, which has already changed. If you're following the news, maybe you know that there is a second quantum supremacy paper coming from China, proving with some optical quantum computer. So this is no longer updated, keep that in mind. But there are very few quantum speed up demos built and achieved by quantum annealing, in very tailored applications. There is no such a thing as quantum advantage for applications. We need to find one application where we say, obviously you're gonna use a quantum computer. That hasn't happened yet. The quantum supremacy things, well, studies that have been proposed are on self-simulation, on just running the chip itself. And maybe you heard about this paper of Google and the whole drama, IBM, Google, 10,000 years, 3 days, whatever. It's still settled. It's still supremacy, right? I mean, you would be nuts to try to run the same problem that they run in the Google quantum computer on a classical computer. It would be nuts. I would claim that we're currently on a work quest to discovering interesting, useful applications of quantum advantage, right? And I'm not the only one who thinks like that. At least people willing to put $22 billion out there to find these applications agree with this assessment. So what can we do with this? Well, we're talking about optimization, right? We have on the left side classical methods. We love our branch and bound, polyhedral theory. We love our global optimality guarantees. We have very efficient codes out there, but we have this exponential complexity that is always like this worst case complexity that's we might encounter it, right? On the right-hand side, we have quantum methods, which are based on this least energy principle. If you look at them from an optimization lens, you would say, these are heuristics, these are limited in hardware size, but they obviously have potential. So we better look at them. Not only that, but let's say that you don't want to go quantum. Yeah, I mean, anything tiny, cold enough is quantum, but building these machines is hard. What can you do with the existing infrastructure? What if you want to have a specialized piece of hardware to solve these problems? Well, there are existing alternatives to solve QUBO through specialized hardware. So from graphical processing units, tensor processing units, to oscillator-based computing, computing with light, computing with, you cannot imagine the number of people who are trying to solve Ising models or QUBO models faster, right? So how can we take advantage of this? Well, going back to MINLP, one approach is, I can tell you, you can transform any MINLP into a QUBO, right? If you have continuous variables, you discretize them. If you have integer variables, you binarize them. You do a binary expansion and that's it. If you have nonlinear equations, you quadratize them. And as long as they are in terms of binary variables, you can do that. If you have constraints, you penalize them, right? And that's it. You starting from an MINLP, you end up in a QUBO. Now, one thing is you're able to do this. The second thing is, would you like to do this? And short answer, I think that you shouldn't do this, right? Basically because they induce growth in the problem size that you already have limited resources. You cannot assume that you can just increase the size of your problem arbitrarily. And this actually lead to quite a lot of growth. And if you have ever worked with constraint optimization problems, you know that softening the constraints, putting them into the objective, you need to be careful about the penalization factors, whether you're actually passing violated constraints. Oops, sorry, something popped up here in the chat. Am I running out of time? I'm sorry. If I am, sorry, I cannot see the chat.
You have a little bit more than around 5 minutes, a little less than 5 minutes left, let's say.
Oh, that's plenty. So what's the answer, right? Let's use decomposition. We have already seen success cases where we take advantage of sub cases of MINLP that can be efficiently solved. In the previous case from outer approximation, we can efficiently solve MILPs, we can efficiently solve continuous NLPs. So why don't we design decomposition algorithms that take advantage of the fact that we might have alternatives to solve quite efficiently QUBOs, right? And we can leverage all the things that we learned in the past, we can apply it back here. And we're not the only ones who are thinking about this, right? There are proposals in Lagrangian decomposition, ADMM, and I would like to talk about tested computation because that's something that I consider quite cool. So you already saw the left side of this plot. Let me talk about other kinds of classical methods, which are not that best known, not as well known. So these are methods based on algebraic geometry, methods based on test sets, and algorithms based on augmentation. Basically, starting from a point in the lattice defined by the integer values, you can go through and basically jump in this lattice from feasible solution to feasible solution without relying on the continuous relaxation. These also have global convergence guarantees. There are very few implementations out there. I would like to shout out to 42, and I think that that one of the developers is in the audience. So it's a great tool, but there are not many, right? And So it's quite limited. But something quite interesting here is that you have something called polynomial oracle complexity once you have to test it. So what is that? We have this set of constraints, ax equals b. X is obviously 4-dimensional, but I'm doing a projection on x1 and x2. And each one of these points are the feasible integer solutions, right? So given an initial solution, let's take the one in this corner, an oracle that compares the objective value from two solutions. So comparing this and this and saying, oh, this one has a better objective. And the test set, which is a set of directions, which I haven't defined yet, you can do stuff. So what are the directions and what do I mean with stuff? So if you have a convex objective, the test set will point you into directions where to improve it. And if none of those directions improve the objective function, you're sitting at the optimal solution. So, and this test set only depends on the constraints and can be computed in this particular case for equality constraints with integer variables. Short example, that's your objective. You want to be as close as possible from the center of the circle. You start in here, you look at these 3 directions, and you can go up here or here or here. Let's say that you take this step, and then you compare against the directions, and you end up in the optimal solution. And the number of steps that you need to take is polynomial with respect to the size of the problem, grows polynomially. So you're going to stop me right there, and you're going to say, wait a second, you're giving us a poly algorithm to solve an NP-hard problem? Sure, right? And the answer is no. Where is the complexity? Obtaining those directions. That is exponentially hard. So how do we deal with this? At the quantum computing group at CMU, we came up with a way of computing those directions through QUBOs in an algorithm that we like to call Gamma, Graver Augmentation Multi-Seed Algorithm. I know I'm running out of time, and I knew I was going to run out of time. So I'm only going to show some cool results, which have to do with this particular problem called the cardinality constraint quadratic problem, right? Quadratic objective function, super easy equality constraint, only integer variables. This here is an implementation, not actually relying on the quantum computer. We can talk on the limitations there, but actually inspired on this hybrid quantum algorithm, we went back into classical optimization and said, oh, look, we could do cool stuff, right? And cool stuff in this case means 100x improvement compared to Gurobi. So why do we care? Well, I mean, why do someone as applied as I care about these problems? They have applications in ML, in chemie, in facility location, molecular energy, portfolio selection, right? So maybe just to wrap up, what I think can be done in the future, this match of novel mathematical models with unconventional computings and hybrid algorithms is something that we better be looking at, right? I mean, we have new ways of solving these problems. We might need new ways of writing down the problems, and we can get some improvements in runtime or solution quality. Why, again, someone as applied as why would I care? Because I really care about energy-related problems. Optimization of energy systems is something that I have worked on. I feel that that's an important problem that people should be looking at. And I think that the current models are still limited with respect to, I mean, there is a gap between what we can model and what we can solve. So obviously, closing this gap is in everyone's interest, especially in such a critical topic like energy, right? Finally, some conclusions, some acknowledgements. Thank you for your attention. I'll be happy to answer some questions.
Is that a question? Can
Hey,
you
Mark.
compare the Fujitsu digital annealer, which you showed a picture of the chip, to quantum annealers such as D-Wave? And Fujitsu just says it's quantum inspired and has a lot of connectivity, but doesn't really seem to say much more about than that.
So yeah, maybe related to that question, obviously the amount of material is huge. Thanks to Alex that already gave a shout out to our lecture on quantum integer programming. We have all the videos, all the slides, all the codes even out there. So feel free to go into that. Speaking of, so Fujitsu is a Japanese company. which has developed a chip which is called a digital annealer, and it's a chip which solves these icing problems, but actually not encountering many of the limitations that quantum annealers have. It's fully digital, so it doesn't rely, it tries to simulate quantum behavior by implementing algorithms in there. I haven't used it much. I know that people at Toronto have access to that machine. I have played with similar devices. I can tell you that, I mean, there are pros and cons. I would claim, for example, that the connectivity issue that you were bringing up, it's a critical thing for quantum annealers. The fact that maybe just for everyone to know what I'm talking about, not in these QUBOs, not every pair of variables can be connected to each other. So you need to go through a whole embedding process, which is really hard. These digital annealers don't need to do that. So obviously that's a big win for them. Not relying on quantum, I mean, you can still, I mean, it really depends on the problem that you're solving. These machines are quite fast, though. I need to say that compared to other heuristics, classical heuristics, non-specialized hardware, they are quite good. It just happens to be that maybe not all problems fit into the things that they are able to solve.
Thank you very much. I think that in the interest of time, we are going to thank David and also the rest of the speakers right now, and we will move on to asking more questions on a one-to-one sessions in our breakout rooms. So thank you very much, Alfredo, Chang, and David. Very great talks. We wish you great luck for the job market, which it's going to be hopefully going very well for all of you. Yeah, I will stop the recording now. And I should say that also, I guess while we're in the recording, that Elias and I are lining up a slate of speakers for discrete optimization talks for DOTS for next semester. Stay tuned for an email regarding that somewhere closer, probably to the end of December or closer to the start of January, but they will be happening roughly once a month at the end of the month, the last Friday of the month at 1 p.m. Eastern time. That's our current plan. Of course, everything is subject to change in the world we live in. So again, thank you very much for coming, and please stick around for the breakout rooms that will be happening right now.
Can I say